Hi everyone. Before we get started, I have a question for you. We've been going through the first chapter of Rudin's book, Principles of Mathematical Analysis. Now, what we're working toward here is trying to understand the proof of Fermat's last theorem. The problem is our foundation is very porous, has all sorts of holes and weaknesses in it. So what I want to do is shore up our foundation before we go on to the harder stuff. So that's what we've been doing here. And I've been thinking that the next thing to do that I wanted to do when we're done here, which we will be soon, is to go over multivariable calculus. And that's important because complex analysis is very similar to multivariable calculus. It's really better if we have a firm grasp of multivariable calculus before we move on to complex analysis. But I've been really enjoying this book, so I'm wondering if anyone would like to continue learning more about real analysis before we move on to something else. So after this, we learn more about like topology and compact spaces and things like that, and then sequences and series and some other things. And it would be fun to do, but I think that it's a little bit tangential from what we're actually trying to do here. So I don't know if it's worth doing right now. We could always come back to it if we need it. But if anyone wants to do this rather than multivariable calculus and then moving on to complex analysis, I'm enjoying this too. So we could just continue with this and see what happens. So please let me know in the comments if you would like to do more real analysis rather than multivariable calculus and complex analysis, and then moving on to modular forms and elliptic curves. Let me know. So we're about to finish the proof that the theorem that we're trying to prove is that every real x greater than 0 and integer n greater than 0, there is one and only one real y greater than 0 such that y to the n equals x. That's what we're proving. That's what we're in the middle of proving. And so I just want to recap quickly what we did last video to set up for what's left now. So we're looking at a set E, be the set of all t such that t to the n is less than x. That's the set that we're examining. So first we showed that E is not empty, and we showed that E is bounded above. That means since real numbers have the least upper bound property, this set has a least upper bound. So we let y equal the supremum of E, and what we want to prove is that that number, the supremum of this set, is the root of x. Okay? So one last thing we did in the last video was, in order to prove this, we're using an inequality that we proved in the last video, which is that b to the n minus a to the n is less than b minus a times n times b to the n minus 1. We use this in order to prove, we're going to use this in order to prove that y to the n equals x. So what we have left to do in this video, the way we're going to prove this is, we're going to start by assuming that y to the n is less than x, prove that that's not possible, and then we're going to look at y to the n is greater than x, prove that that's not possible. So if if one thing is not less than another, it's not greater than another, then the only thing left is that they are equal. So this is what we have to do today. Now, here's where it gets quite difficult to wrap your head around. So first, I'm just going to show you the math, and then we're going to go back over it and try to understand it. So let's assume the opposite, that y to the n is less than x. Choose h so that h is between 0 and 1, and h is less than x minus y to the n over n to the y plus 1 n minus 1. Okay? Put a equals y, b equals y plus h. Then, now we're going to use the inequality that we just showed. So we're just going to plug these into what we just established and see what happens. So we have the y plus h raised to the n, that's b, minus y to the n, that's a, is less than b minus a, so it's less than y plus h minus y times n times y plus h to the n minus 1. So obviously the two y's are going to cancel, and we have that equals h times n times y plus h to the n minus 1, which is less than hn to the y plus 1 n minus 1, because h is less than 1, so this is going to be bigger than that, is less than x minus y to the n. The reason for this last one is this is the denominator. So if we multiply the denominator by h, we have hn to the y plus 1, and then that's going to be less than the numerator, which is x minus y to the n. Thus, y plus h to the n is less than x. Okay, y plus h is less to the raised to the n is less than x. That means that y plus h is going to be an e, because that's the definition of e. Okay? So we know that y plus h is greater than y, because this is positive, so y plus h is greater than y. But remember, we started with the fact that y is the supremum of e. So there should be nothing in e bigger than y. But we just found something that is bigger than y. Y plus h is bigger than y, and it's still an e. That means that y can't be the supremum of e. So something's wrong. That's a contradiction. So y to the n cannot be less than x. Okay? That's the proof of the first half, that y to the n is not less than x. I don't think the math is actually that hard to understand, but I want to go through this and try to understand what in the world we just did, because that's really the point. The first thing that we can notice is that x minus y to the n is coming from the assumption that y to the n is less than x. We've done this many times, where when you have an inequality like that, you subtract one from the other to find out the distance between them. This comes from the inequality that we started with. I should write that down. B minus a to the n So this is clearly just coming from here. The thing that we have to think about is, what is the least upper bound? Because you remember in our original example, we had if p squared is less than 2 in the rationals, then this set has no upper bound. And at the same time, there is no least upper bound, because no matter how close you get to this line, you can always find another rational number that's even closer that's also an upper bound. There's no least upper bound. You can always find one smaller. So what we did is we put in the least upper bound. So what we're doing here is we're saying that y is the least upper bound of the set E. And we're saying like, okay, so let's say that y raised to the n is not x, does not equal x. In fact, it's less than x. That means that in some way, you're going to be able to find, like if this is a y, you're going to be able to find something a little bit bigger that's still inside E. And so the y plus h, that's what we're doing here. We're doing the same thing that we did back in the beginning, where we're looking at, if we assume that it's not the least upper bound, then you're always going to be able to find one just a little bit bigger. And the way that you use this least upper bound property is exactly in that way. You assume the opposite. Assume that it's not the least upper bound. If it's not the least upper bound, that means that there's still room between y to the n and x for another one. So that's what we're saying. So we need to actually construct that number, because the question is, we might be able to find one here. So let's say we find y plus h is between y to the n and x. Y plus h to the n is between y to the n and x. Okay, well that just means we chose the wrong supermum. So maybe this is the supermum. The point of what we're doing here is to say no, because we defined h using the supermum. So you can pick the supermum to be whatever you want, however close you make y to x. If y raised to the n is less than x, then we're always going to be able to find one that's just a tiny bit bigger, that's still going to be inside E, less than x. And the way we do that is we take the difference between these two, and then we divide it by a positive number so that it's going to be even closer. So that if this is y to the n and this is x, no matter how close together those are, we take this difference, divide it by this number, we're going to get something even smaller, add that little bit to it, and we're going to be inside this difference. And what this does is this constructs a number that we can prove is always going to be inside E, and it's always going to be also, though, greater than the supermum, meaning that there's a contradiction, so that this is simply not possible. Now what we're going to do is the same thing on the other side. So, okay, fine. The supermum raised to n cannot be less than x. Maybe the supermum raised to n is greater than x. Okay? So that's what we're going to do now. So assume that y to the n is bigger than x. We're going to reach another similar contradiction, that if y is the supermum of the set E, then this isn't going to be possible. So if y to the n is bigger than x, then we're going to again find another number that's even closer, that is still going to not be an x, but will be less than the supermum, so it should be an x. So this time, let's make k equal y to the n minus x over n y to the n minus 1. So this is what we're setting k as. So again, this is going to be the difference between y to the n and x, and then this is the thing in that identity. It's less than when A is less than B. Okay, so this is this. Setting k this way, then 0 is less than k is less than y. So k is bigger than 0, same as before, because this is bigger than this, so this is positive, y is positive, n is positive, so all of this is positive. So k is bigger than 0. K is less than y because, so we have that, we know that x is greater than 0, right? X is positive. So we know that that k equals y to the n minus x over n to the y, n minus 1. If we just add an x to the numerator there, we know that x is positive, so all we're doing is we know that this, if we add x here, it's obviously bigger than this one. And then we can just cancel the two x's. So we have yn over n to the y, n minus 1. That means we can clear everything here except 1, and we have y over n. So k is less than y over n. So then n is also positive. So if k is less than y over n, then k is also less than y, because n is positive. So if you're dividing y, it's going to be smaller. So if you just multiply, if you multiply this by n, then y is going to be even bigger. So clearly it's going to be bigger than k. So 0 is less than k is less than y. And then note one more thing. Let's just do this here. So if we have k equals y to the n minus x over ny to the n minus 1, if you multiply both sides by the denominator, you get that y to the n minus x equals k n to the y, and a times y to the n minus 1. So now we're going to do the same thing we did last time. We're going to use this inequality to see what happens with a certain t that we choose. So if we let t be greater than or equal to y minus k, okay? So with this, so basically using b is y and a is t, we have that y to the n minus t to the n is less than or equal to y to the n minus y minus k to the n. So now we're using the inequality. Y minus k is less than so this is b, this is a. So here's b minus a, and then that's what's left over, right, of b. So we cancel these, same as we did before. Wait, is that right? No, I wrote that down wrong. It's y minus y plus k. So these cancel, and we're left with k equals ky to the n minus 1, which we set up here equals y to the n minus x. So the hardest part to understand here, I think, is this one. So to see this, we have that t is greater than or equal to y minus k. Just do it over here in the corner. So t is greater than or equal to y minus k. That implies that t to the n is greater than or equal to y minus k to the n. That implies if we multiplied both sides by minus 1, we would have that minus t to the n is less than or equal to minus y minus k to the n. Then if we just add y to the n to both sides, we have y to the n minus t to the n is less than or equal to y to the n minus y minus k to the n, okay? And that was what we had here. And then the rest of them I think are more clear, because this is the inequality that we started with, and then from there we just cancel the y's, and then the rest of it is what we came up with. So what we showed here is that y to the n minus t to the n is less than y to the n minus x. So we just showed that y to the n minus t to the n is less than y to the n minus x. That implies if we cancel these, we have that minus t to the n is less than minus x. That means that t to the n is greater than x. That means that t is not an element of E. So then it follows that y minus k is an upper bound of E. So why is this true? What we started with was that t was greater than or equal to y minus k. And what we just showed was that if we start with that, then t is not going to be in E. And what we started with was just that t is anything bigger than y minus k. So that means that anything bigger than y minus k will not be in E. So y minus k is an upper bound because anything, it's a bound, because anything bigger than that won't be in the set. So now we're at the same point we were before. That means that y minus k is an upper bound of E. Now I think we can figure out what the problem is. Y minus k is an upper bound of E, but the problem is we started by saying that y is the least upper bound of E. There should not be an upper bound of E smaller than y, but k is positive. That means that y minus k is less than y, which means that it's smaller than the supposed least upper bound. That means a contradiction again. That means that y to the n cannot be greater than x. Okay? So we're done. We've shown that y to the n cannot be less than x, and y to the n cannot be greater than x. There's only one possibility left, which is that y to the n equals x. So what did we arrive at? What have we done here? We've shown that every positive real has a positive nth root, no matter what n is. And specifically, that root is the least upper bound of the set that we started with, which is saying that if you take the set of all real numbers such that y to the n is less than x, so this would include the one that we started with, which would be that p squared is less than 2. Then the supremum of this set is going to be the nth root of x. And why was this so hard to do? What we started with was only to say that this number is not in the rationals. So we started by saying the square root of 2 is not in the rationals. Well, what are we going to do about that? So then we examined it a little further, and we looked at this set, and we saw that there's another way of looking at this problem, which is that this set does not have a least upper bound. No matter how close you get this upper bound, you can always find one that's even smaller. So we're like, okay, let's fix that problem. Let's make it so that, let's just define it so that every one of these sets has a least upper bound. We did that. That's what we've been talking about for the last few weeks. But even having done that, we didn't exactly address the original problem, which is that we want there to be a number that is the square root of 2. So what we've been working on is making it so that every set in the real numbers has a least upper bound, but at no point were we ever actually talking about the square root of 2. So the last thing we needed to do to sort of come full circle is show that with this property, now that we have a field that has where every bounded set has a least upper bound, we can actually use that to find a root so that now each number, each positive real number in that field has a root. And in order to show that, in order to construct that number, we use the least upper bound property. So it's very interesting to think about because what we started with is in some way bigger and deeper than just the roots. But then even having done that, as simple as it is to say each set has a least upper bound, we didn't solve the problem yet, and we had to go through all this in order to show that in fact that's true. There's one other thing to show here. A corollary. The first math class I ever took at Berkeley was a grad student who was actually British, so he would say corollary. In my head, I'm always thinking corollary, even though, of course, it should be corollary. So the corollary is that if A and B are positive real numbers, and n is a positive integer, then the nth root of AB equals the nth root of A times the nth root of B. So this is just one of those results that we need to show, and it comes from what we just did. So if we let alpha equal the nth root of A, beta equal the nth root of B, then AB equals alpha to the n, beta to the n, and we already know that this is alpha beta to the n because multiplication is commutative, right? So this would be A times A times A we can rewrite that as AB, AB. Okay, so alpha to the n times beta to the n equals alpha beta to the n. We already know that, so that means that AB equals alpha beta to the n. So then using the uniqueness of the theorem, which says that each root is unique, we just showed that AB equals alpha beta to the n. So we know that alpha beta is the nth root of AB. So we can say that the nth root of AB equals alpha beta. And we know that alpha is A to the 1 over n, and beta is B to the 1 over n. So that's the result. The nth root of AB, which is alpha beta, equals A to the 1 over n times B to the 1 over n. It requires the uniqueness of the last theorem because to show that this is the only one. So this is the one that we're talking about. Okay. Okay, so we are all done with our examination of the real numbers, the result of all of our field axioms and ordered field and the least upper bound property. Now we're ready, finally. The only thing we haven't done is actually prove that this field that we've been talking about, the real numbers, actually exists. So now we're going to have to actually show that we can make a field that actually will have the properties that we've been talking about. So that's what we're going to do next. That's the Dedekind cuts that I've mentioned a few times. Then we're going to show something that is nowhere else on YouTube as far as I know. We're going to show that there's in fact only one such field. That's a really long, really interesting proof that will be fun to do. And then we'll be done with real numbers and we'll move on to complex numbers. Thank you. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.